Greetings everybody. My name is Murali Balasubramanian. I am with Fiat Chrysler Automobiles, and today I am going to talk about Metamodels and how it is being increasingly used and in automotive industry, specifically for R&D. And I am going to focus on safe and efficient automotive structures and how Metamodel application is increasingly being used to speeden up the process. Little bit about myself. I graduated from this place 26 years ago in mechanical engineering, BTech. Did my masters in mechanical engineering from Clemson University, and I have been in R&D automotive for almost 24 years, so quarter century. So I have seen a lot of the progress made by the automotive product development, research and innovation, specifically from different points of view. Little bit about my company. We are the 8th largest automaker in the world. We have more than 164 manufacturing plants. We sell close to 5 million vehicles every year, and we have around 84 R&D centers. And some of the brands that we sell, some of which is known here. Fiat is well known here. Recently Jeep has made a splash in India with Jeep Compass. Apart from that, we have other brands which sells worldwide. Specifically Jeep and Fiat are the key brands that is known here, and of course also recently the Abarth brand. Where I work is in Chennai. We have the 3rd largest R&D center out of the 84 centers. It is located in Chennai in Perungudi, very close to our campus here, and we have a fairly large R&D team there, more than 1000 people, specifically working on most of the Fiat Chrysler mass production programs, vehicle programs. So that way we have a very rich exposure to the R&D activities here in Chennai. I am very happy to be talking to you regarding Metamodels, because one of the things that is relatively less known, where automotive industry is going through sort of a revolution in terms of, you have heard about autonomous vehicles, you have heard about digitalization in terms of connectivity, infotainment, connected vehicles, smart manufacturing, advanced material use, and of course the use of AI. The use of AI is becoming increasingly prevalent in the automotive industry, and I must say that we are not the only ones. Pretty much all across the board are investing heavily in AI tools, and Metamodel is one of the popular derivative of AI applications, which we will talk about. So I am very happy that Professor Payani and his team are conducting this course, because this is very important, I believe, especially looking at the future, and not just the future but even current requirements in the automotive industry. Just to give you a certain statistics and facts, again this is publicly available data. Almost $30 billion, around $30 billion has been invested in AI, and most of the investors are in the tech giants like Google, Amazon, and of course automotive industry is also a high adopter of AI tools and AI applications. And typically what type of activities in the automotive industry happens with the help of AI. So engineering and R&D is in the forefront, and I will explain how as an example. Of course operations, supply, manufacturing, distribution, these are other areas where AI is being increasingly used. So why is it that we use AI in engineering and R&D? Because we want to get solutions faster, speed to market. We want to do things, get to optimized solutions quicker, fewer what we call iterations, and Professor Payani is going to talk to you a lot in detail about optimization. But I think when we talk about optimized solutions, we are talking about where we are able to bring it to the market at the most efficient cost, weight, in terms of performance. So, and the help of Metamodels, which I am going to talk about, we are able to do a lot of upfront, when I say upfront, early in the program, advanced stage of the program, we were able to get a lot of quick answers, right directions, Imagine you have a signpost very early in your trip to tell you where to go, you can go obviously to your destination faster. So, that is one of the big advantages of metamodels, and I am going to give you some examples, and this is a classic application of AI, and obviously coupled with machine learning we are going to make sure that as we progress forward the metamodels are going to be more and more valuable to us for advanced engineering activities. So, one of the classic applications of metamodels is going to be or is being used in what we call the vehicle performance space. What is this vehicle performance? There are variety of things that we need to achieve to bring the vehicle to the market. For example, we need to achieve safety, we need to achieve safety regulations, safety targets. That is an important for every geography, they have their own federal regulations, safety regulations, standards that we need to meet, and for FCA safety is one of the highest priority items for in terms of vehicle performance. Apart from safety, we need to have aerothermal performance or heating, ventilation and air conditioning system. Any of these the aerothermal aspects are very important. So, that is an important physics that we deal with day in and day out. The other ones, fuel economy, of course, fuel economy performance, everyone's after the most efficient performing and fuel consuming vehicles. So, that is one of the key parameters for vehicle performance. Apart from that, ride comfort and handling, obviously you want to have a comfortable ride on the road for both driver feel as well as the passengers in the vehicle. And of course, we want our vehicle component systems to live through the cycle, life cycle of the vehicle and beyond. So, we actually design the vehicles to and the systems and components within the vehicles to survive the life cycle and beyond, and that is through what we call durability science. So, durability sciences will ensure that we are subjecting the vehicle systems and components to the various loads and see if it lives through the fatigue cycle, through the stresses, and we actually take the vehicle on the road virtually. So, this vehicle performance, what I call, of course we test it once a vehicle is prototyped, but most of the times we develop the vehicle advanced stage of the program through what we call virtual simulation. Virtual simulation is where we do everything on using computer software tools, and these tools are specifically fairly expensive and resource wise it requires fairly complex or fairly skilled resources, and then of course we need high performance computing facility to ensure that we use very complex simulations and get results out of it for driving our designs or design solutions, or what we call what is the optimum configuration we have to go towards. Now, this virtual simulation, just to give you a sort of a idea, I will play a video of how many safety related structural events that we have to look at for a vehicle to pass the performance tests. So, for example, this would be the frontal impact, rear impact of different speeds, you have impact with a pole, you have an offset impact where your only partial of the vehicle is impacting, and then you have narrow offset impact where you have only very narrow portion of the vehicle impacting, you have car to car impact side and front, then you have things like rollover where the vehicle tips over, rolls over and you have other events like side impact, and then complex events that goes on as a combination of the ones that I spoke about. So, and these are different in different geographies because of the road speeds. For example, road speeds in India would be much lower than the road speeds in the European autobahn or in the US highways or expressways. So, in that sense, vehicles these days are coming off global platforms, which means they are being designed common structures and content common most of the time, but sold in multiple geographies, which means these vehicles more or less most of the time have to meet standard regulations across the globe, which means multiple regulations. So, safety is one of the top items for us and for FCA, and in fact I would say for most of the automotive industry, saving passenger lives in a crash event is one of the most important ones. In fact, active safety is where we prevent, and there is a lot of research for preventing crash in terms of sensors and collision detection, proximity sensors, things like that, which are being increasingly not only used to prevent accidents, but also being used for autonomous vehicles, self-driving vehicles eventually. So, it's kind of going hand in glove. The other interesting activities we may be doing could be like improving fuel economy performance. There are multiple ways we target a vehicle to improve its fuel economy. One is targets make it lightweight, and this is a classic optimization problem, optimizing, minimizing structural weight while not compromising any performance. When I say performance, I alluded to the different performance aspects like safety or ride comfort or aerothermal performance or the durability or reliability for the vehicle to live through the life cycle. So, while we meet all that, we need to make sure we do not waste material in the vehicle. So, optimizing weight is going to be one of your classic applications or desires or objectives for your structure, automotive structure. Apart from that, of course, we have things like drag reduction using active and passive aerodynamic features in the vehicle, which can then minimize the energy expended by the vehicle navigating through traffic or navigating through the roads. So, of course, we have tools specifically for each one of these things. We have tools to do optimization, we have tools to do aerodynamics, we have tools to do fuel economy calculations, but again all these tools require time, require software, require skilled resource, require modeling, virtual models like building finite element models or building vehicle dynamics models or building some sort of a mathematical model, numerical model, could be even finite volume or CFD type models. So there is a lot of resource, time and money spent in doing virtual simulation. Okay. So, which is where I think I want to give you some examples. For example, this pedestrian protection is one of the important safety event, which I did not show in the earlier video, but it is important that the vehicle minimizes the injury to the pedestrian. So, we have a simulation where, for example, on the lower side I have shown you here is like the head of a typical based on statistics, we pick the most common head form and then we impact that head form on the hood of the vehicle. This is a simulation activity actually, and then we measure what is called HIC. HIC is a head injury criteria in terms of forces, and that becomes one of the measurement response parameter. So, we supply the head form with some motion and speed and impact parameters based on statistics again that we get from testing and then physical testing, and then we simulate it on the computer, and that is where the head form simulation and the HIC is one of the important parameters that we measure. And we try to design such a way that we minimize obviously the HIC, which is the head injury criteria. That is one of the things. Apart from that, we have, for example, just like any component of the vehicle, the doors need to be, you slam the door so many times during the life cycle of a vehicle. So, you slam the door, you open the door with gusto depending on your temper and that is going to vary with season, time, and it is not going to be we have to design it for the most calm person to the most aggressive person, the heaviest person to the lightest person. So, obviously we have factors of safety, design factors, and we say let us take a 200-pound guy and let him slam the door at certain speed, which is the worst case scenario, and then we make sure that the components on the door do not fail during the life cycle for n number of cycles. That again comes from the statistics. So, these kind of things we actually simulate, and we study things like output could be here, could be the stresses, and we measure those stresses, and then we also look at the fatigue. Similarly, for noise and vibration, we want to minimize the noise and we want to minimize the vibration felt by the driver and passenger within the vehicle, and those are again using frequency response parameters, modal parameters, etc. So, again I am talking about what parameters we use in simulation to actually talk to these performance parameters. And as I mentioned before, aerothermal is important obviously to ensure that we have enough aspiration in the underhood chamber for the engine to cool, we have enough climate control within the vehicle, and it also ensures that we need to do it efficiently, again optimizing the flow pattern, optimizing the thermal characteristics. These are, I use the word optimization a lot, which I think will lead well into Professor Payani's lectures. I think everywhere we talk about achieving a particular goal in terms of a structural performance or a thermal performance, I think we are talking about achieving it, achieving an optimized goal or optimized solution. Again we want to minimize the material expended on creating that particular structure or vehicle content, or try to also reduce the weight and cost. So, we call it typically cost, weight, investment reduction, minimization. So, we try to attempt to do that as we achieve our performance goals. Again, most important to achieve the performance goals. While we do that, we want to cross functionally make sure that the vehicle is manufactured at the lowest cost at a particular acceptable lower weight. Now, I said why do we need metamodels? I am going to talk to you about metamodels, but I told you some of our constraints. For example, our CAE models or FE CFD models typically currently uses about million grids, and it takes sometimes anywhere between 3 to 6 weeks to build that model. So, we are talking about spending 3 to 6 weeks of a live program time, and this is not happening in a program life cycle. It's going to run multiple milestones or multiple cycles, and each time you spend anywhere between 3 to 6 weeks building your complex numerical models. And just to give you a statistic, this is very approximate, around 1000 simulations a day is not at all uncommon. It's probably much more than that in some cases, but something in the neighborhood of anywhere between 500,000 to a million simulations every year is something that is very normal these days. And we are talking about simulations that run for 2 hours on the high performance computing system to sometimes even all the way up to a week, at least 5 days, 6 days to run a simulation like a CFD simulation. And simulations are very expensive. Typical budgets could range anywhere between $250 million annually, and each cycle to come up with the entire performance evaluation, all the things that I talked about, it may take anywhere between 8 to 12 weeks for every cycle to achieve some sort of report card, if you will, for that cycle, design cycle. It might take 8 to 12 weeks. And why we do virtual simulations? Because it's happens to be much cheaper than doing physical testing. You need to proto the vehicle and test it. That's even more time consuming, even more expensive. So, we are talking about an order of magnitude lower costs for virtual simulations, but even virtual simulations are expensive. There is a lot of data transfer between workstations that users use to simulate and the high performance computing environment. So, there is a lot of data transfer. Much of the data interestingly gets discarded because we look for what we want, we get that information, rest of the data is discarded. So, we spend a lot of money generating data from our simulations. For example, I want to generate the stresses on the door panel for a slam event, and I only want to look at the high stress zones. I pick the high stress zones, rest of the data goes discarded. So things like that, a lot of the data that we generate using simulations get discarded, and each simulation we have multiple response parameters. We look at sensitivities of those responses so that we understand the behavior of the system, and we try to use visual animations, some sort of 2D plots, 3D plots, etc. to understand the behavior. But interestingly, none of the FE simulations or CFD simulations actually arrive at a functional form between what we call performance responses and the design parameters or variables that we are tweaking or we are changing to arrive at the required performance. So the functional form relationship is not apparent, it does not, we do not target those, we look for instances, design instance and the corresponding performance. So what is not achieved is a functional form relationship, and each time we track only one design at a time. So once we get the information from one design, we try to go towards the improved design from evaluating that one design. So what happens when you do evaluate for one design is that you are looking at the perfect vehicle that is manufactured as per design spec, which never occurs because of manufacturing tolerances, because of material spec tolerances, because of assembly tolerances. So all of these things, there is actually vehicle to vehicle variation on the design, even if the design is frozen as we call it, or design is, we have frozen the design spec, but the manufactured design is not the same as the design spec, there is a variability. So we do not have much or shall we say we are doing it right now, but the variability is an important item that we need to track, not only to ensure that we look at the variation in the response because of the tolerance variable, because of the variabilities, but also we need to arrive at robust design which is insensitive to the variabilities, which is where we use tools like design for Six Sigma and etc. Interestingly, many of these data that we look at many times are simple data like plots, ASCII data. So it is not encrypted binary data all the time. So interestingly, we can use, we discard, a lot of time we discard this data, but we can really use them, and I will show you how using them we can get much faster solutions using metamodels. As an example, let us take a case study of one of our vehicles where we are looking at the frontal crash, where the vehicle is slamming into a rigid wall at certain speed. We have different speeds for different geographies, like I said, so I will not get into the details of the speeds, but the event here is to ensure, obviously in an event like this you want to ensure minimum intrusion into the cabin, which means minimizing the injury to the occupants, and essentially most of the energy needs to be absorbed by the front end of the vehicle. So the front end, when I say front end, we are talking about the one that is being crushed here. The energy management becomes a very important physics aspects, and there are several things that we need to engineer to arrive at the desired physics or the desired characteristic structural behavior, things like sections of the key members, the geometry of the sections, the material used, the thickness of the parts which are sheet metal, how they are stacked up. All these becomes, what shall we say, tunable design parameters or design variables that we can actually change to arrive at the desired performance. Now if we know what those design parameters are, and then if we know the desired responses, and we track a lot of things as what we call responses to arrive at a desirable safe structure, and we have at least 13 to 15 parameters, but we look at most critical ones, response parameters, to ensure that we have a safe structure, and I have enlisted some of them here. Obviously we have targets for each one of this, and these targets change with vehicle, change with the the regulatory criteria and the type of event, etc. So I did not put the numbers to not to distract you from actual, that each one of these response have targets, and each one of these targets is what we call we need to achieve as a performance goal or objective. And the design parameters could be like I have enlisted here, the shape and size, the material spec, and then the part thicknesses of the sheet metal part. So with this as a problem statement, typically what do? We build an FE model of this entire vehicle that takes anywhere between 5-6 weeks, and then we subject this FE model to the appropriate load, which means we have the either the car slamming in, or we have the barrier slamming into the car, and then we look at the behavior and we measure a few things like we did here. We use specific tools such as LS Dyna for simulating this event, and all of these things, by the time we come out with solutions to mitigate any risks, takes anywhere between 8 to 12 weeks. And what can we do about it? How can we make it faster? We can use what we call metamodels. I think in metamodels we and I will show you a small graphic on that, but we actually look at the parametric model of this front end, and then we look at what we call design space exploration, and I think many of these topics Professor Payani will cover in detail, but essentially we are trying to map the response space to the design space and build a functional form relationship, approximate what we call the regression of the response function. So once we do that, we are able to relate each one of these parameters to the design parameters in a way where we are able to understand a relationship between the two from predictive ability, also other aspects like sensitivity, what are the most important design parameters for a given response, etc. So these are some of the things we are able to achieve with Metamodel, and we can do that. Sometimes we are able to do that even before we have an FE model, because we can use a predecessor vehicle which is related to the current vehicle, and we can use parametric models within the predecessor vehicle. So if you have a new vehicle which is coming off the same platform as your current vehicle, you can use parametric models of the current vehicle and project the design characteristics or design spec of the future vehicle, right. So then you can actually use the relationship that you develop using that current vehicle parametric model, response versus design space, and then you can actually arrive at meaningful answers which will help you get to your future vehicle decisions faster. Okay. So interestingly, we did this exercise and we found out we were able to predict using metamodels very close to FE simulations, almost within 2 to 4% mean error. So which is very good confidence in the metamodels to be able to give us meaningful answers. Some of these critical responses, especially maximum of 5 to 6% error is what we were able to see, which is acceptable for making decisions. One of the common used algorithms for crash, especially when you do regression for crash responses, is Kriging, actually Kriging and hyper Kriging, which, so I am going to just show you the application, right. So we can actually, it's actual application of algorithm for a crash analysis that we do. So Kriging is one of the popular algorithms, along with radial based functions are used specifically as algorithms for in the metamodels generation of crash analysis. So just to give you an idea, what can we achieve with a metamodel, and how quickly we can achieve it. In a matter of minutes, I can create a metamodel. Once I create a metamodel, in a matter of minutes I can simulate what the optimized design is going to look like, and typically 25 kg reduction in the front end starting from a given design is very common, and that 25 kg reduction results in about $30 million US savings for a program, because each vehicle you are saving 25 kgs, and if you sell 600,000 vehicles, which is a conservative estimate for some of our vehicles that we sell, we are talking about $30 million in upwards of $30 million savings. So 1 kg optimization or 2 kgs is not trivial. So when the word optimization needs a lot of, directly relates to savings, actually cost savings for the company, bottom line of for the company. So just to give you an idea, so as to give a mathematical flavor to this, so we have design parameters, let us call them x's. We run CI analysis by parameterizing the design. For example, we may change the sections, or we may change the thickness of the material, or we may change the material in the front end of that vehicle that we spoke about for frontal crash, and we build what we call a response surface or regression of the response function with respect to the design variable. Now we may do it for safety, for a crash event, we may do it for an NVH, or it could be for a durability event. Typically we would ideally like to optimize all these responses for and save weight or cost when we look at the design parameters. In the case of Metamodels, since we have response functions, it becomes a multi-response optimization as opposed to what we call multidisciplinary optimization. Multidisciplinary optimization is a lot more complex because it involves different environments you need to run each. Simulation safety runs in a different environment, durability runs in a different environment using different softwares, different times it takes to run a job or a computational simulation. Similarly, so instead of the multidisciplinary optimization is a complex environment, we can actually in Metamodels reduce it to a multi-response optimization. It's 3 functions or 4 functions or 10 functions, and you can go and get very good idea of what your optimized design space or design ranges are going to be. So this is one of the big applications of Metamodels, right. So just to give you a flavor of how the Metamodels work is, let's take this graphic here. On the left, what I call design space exploration, so which means each dot in the left hand side here represents one vehicle design spec. So this dot versus this dot is where you change something in the design. So if I had a vehicle parametric with parameterized design parameters, then each one of these dots represents a different design configuration, and if I were to explore the boundaries up to the boundaries of the design ranges, then I am really doing what I call design space exploration. Why do I do that? For each one of these dot, I do a simulation of that particular vehicle spec for my various responses, not one, but like I said, it could be 5, 6, 10 responses, and I build what I call regression. I build a regression function to represent the response as a function of these design variables. The design variables could be section size, it could be thickness, it could be material, right. It could be any of these changes could be reflected in these dots, a combination of these changes, and I am building a regression function using various complex algorithms that is available in my Metamodel toolbox, if you will, what I call a toolbox. So what you will probably learn in the course is a simple understanding of what we do to explore the design space in order to be able to build an understanding of the response space and then arrive at an optimum configuration, which means achieving an objective in the response space and minimizing certain minimizing the waste in the design, material waste or cost, those kind of things. So This is typically what we do day in and day out, and we are seeing increasing incidence of metamodels in our daily activities. Why? Because metamodels help us make decision faster. We are able to draw a lot of insights into our structural behavior, which are not very apparent when we do FE simulations, because we are actually doing a sort of a functional form relationship between the response and the design. So, it becomes a very useful additional tool to our existing virtual simulation environment. Let me re-emphasize the point here. We are not replacing what we are doing in terms of virtual simulation. We are only augmenting to make decisions faster. So, I have to run a fewer number of CAE simulations if I were to use metamodels along with CAE models. So, which means I am going to reduce my time, effort, computational cost, and therefore, I can actually optimize on my skilled resource. I can make my resources more engineers rather than computational engineers, so they can make engineering decisions. Let me emphasize that metamodels are effective when you make good decisions while exploring the design. So, that is where engineering know-how comes into play, and I think there are standard algorithms to do design exploration, but then supplemented with engineering know-how is when your metamodel activity becomes more and more powerful. And interestingly, these models that we built are sort of what we call machine learning models, which means the more data I provide regarding my vehicle configurations, the metamodel becomes more and more effective, more and more accurate, more and more giving us more and more insight. So, that's pretty much what I want to talk about in terms of an example of how we use metamodels. But metamodels is here, it is here to stay, and its increasing incidence in our day to day development activity is very profound now, and we see almost up to 30% reduction in our improvement in our efficiency in terms of how we can leverage these metamodels. So, just to give you how a metamodel toolbox might look like, it has obviously a sampling engine so that you can sample the design space with parametric design variables. You have a regression engine obviously with advanced algorithms, and you will get exposed to some of these basic as well as advanced algorithms. We have the standard ones like Kriging, radial based function, but also advanced deep learning type of algorithms, and we also use what we call ensembles. We use all varieties of or shall we say our algorithms on the shelf to come up with our regression of our response parameter. Of course, we have optimization engine so that we actually can do optimization within the metamodel toolbox. That is important, and I think at the end of the day we are all trying to get to better solutions which are what we call optimum, and I think starts with the definition of what optimum desirable objective is. So, and that is for us is, like I told you, multiple. We have safety, we have aerothermal goals, we have ride and comfort goals, we have durability goals. So, many of these are actually going to be conflicting. Some may ask you to increase the weight, some may ask you to actually reduce the weight, some may ask you to increase the cost. So, it is going to come down to making some conscious decisions. We have to do what we call trade-offs, and I think we are going to talk about trade-offs in the optimization course, and the trade-offs are done with a lot of engineering background, engineering know-how, but very well quantified by these metamodels and CAE simulations. But metamodels are going to do it much faster, much quicker, and many times we do not have the time. For example, to do a full-fledged transient CFD for a flow through a pipe, it takes few weeks. I do not have weeks to make decisions for my flow geometry and many times we do not use those simulations, accurate simulations, that is where things like metamodels can come into play, where we are able to get time bound answers. Visualization is important because we are dealing with data, sometimes abstract. The metamodels does not understand what this data means, but tries to relate the data that it has. So, visualization becomes an important toolbox that we need to augment to our metamodels, because we need to visualize we are used to, as engineers, visualizing our structures, how it behaves, animations like I showed you, and we need to be able to get some level of comfort for the user of these metamodels, and the visualization toolbox plays a key role in trying to elaborate or visualize, provide visual context to what we call the metamodel outcomes, outputs. So, things like sensitivities, error metrics, noise plots, design variable correlations, response correlations, things like, there are a lot of things that we can do with visualization. So, this a typical metamodel configuration. So, this is what we use, sort of a variation of this, but it is very prevalent now in the industry and augmented to our current virtual simulation environment, and becoming more and more integral part of it. So, I am really happy to talk about this because it is very contextual, it is very contemporary, I would say it is futuristic also in a way, because right now we are talking about AI applications, machine learning, metamodels as in its infancy actually, and some are a little bit more evolved than the others, but most people are getting into this, and when I say they are actually getting into it, they are not matured, and so it is perfect time for this course, I believe, and I really applaud Professor Paini and IIT Madras for bringing this out, because the automotive industry is going through a revolutionary phase, and AI is becoming one of the pillars for those revolution, and if we are not aware of this, then we are going to be left behind in terms of, especially as core engineers involved in R&D activities and research and innovation activities, and I think really this course will definitely benefit us in giving us that right kind of kickstart, if you will, and we are looking, when we look at engineers, we are looking at engineers with certain skills which are different from what it used to be today. So, we are looking at people who understand how to understand algorithms, understand data, how to work with data science aspects. So, these are the kind of engineers we are looking for going forward, and I think I really applaud Professor Paini and team for this course, and I wish him and the students all the best going forward. I hope that I can contribute in any which way to make sure the course gets as effective as it can be, to help the students transition from the books to the actual R&D labs, hopefully. Thank you.